The following is a conversation with Daniel Ruberman, a professor of mathematics at Brandeis University. His research span low-dimensional topology and knot theory. I hope you will enjoy this conversation. This is Back to the Stone Age. Danny, do mathematical entities exist independently of our human minds? And what implication would it have the view that mathematics and its objects are sort of independent of our own reality? In brief, is mathematics invented or discovered?
Well, we can't know that because how else would, I mean, there's the paradox. We're only discovering, we're only seeing these things with our own minds. So I can't give you an, an actual answer to those questions. But if you're asking me what I believe, um, I think there's some independent reality to some mathematics. I mean, I don't imagine. I think it's part of the world that if you take a circle and take any system of a line and as the Greeks tried to do, measure both the line and the sort of the diameter and the circumference of the circle, they would be in a certain ratio, and it would be the same ratio no matter what you did, no matter what the where you did it and so on. And so I just have a hard time believing that that would shift somehow. So, again, I don't know any other universe. So I think in our universe, that's a universal truth. So in that sense, that concept, which we call pi or however, whatever letter we use for it, uh, that's a universal truth and that's a universal thing. So I don't know. I don't think that could be simply a creation of the human mind. Now, the question of whether some other alien species or something like this would think to measure those two things, I would think that anybody would, but maybe not. I mean, I don't know. That's impossible to know. So, but the question is, can you extrapolate from that? And again, I think the concepts of numbers are, I mean, there are things that sort of naturally divide themselves into groups of a certain size. And again, it's a fact that, again, that comes out of set theory or axioms that if you have things of different sizes, the way we would define them, you can't put them into one-to-one correspondence. So in other words, counting exists, and I think that exists outside of human, outside of humanity. So in that sense, when we discovered how many hundreds of thousands of years ago to count things, that there was a difference between one thing and two things, or and started to give names to those, I think we were discovering something that was part of nature. So it's a long route from those things to those basic things that you just see as I think as actually part of nature to modern sophisticated mathematics, to analysis or algebra or topology and all the things that mathematicians study. But I think you can trace a route that way. It's a hard question to answer, I guess, is the real thing. But I think if you trace the chain of logical implications, you'll see that, well, all those things that we're defining in our papers or defining in our classrooms, those things somehow exist because we started with the numbers and so on. So I guess I'm somewhat surprised. I'm somewhat surprised by the answer that I'm giving you. I think I was prepared to say that we invented it all. The way that but that's this is sort of philosophical side to it, and then there's a psychological side to that question. The psychological side of that question is, did we invent these things? And I think yes, because I don't think every society would come up with the same mathematical concerns. I think some people just, I mean, you can even see that from country to country. I mean, even on our relatively small Earth, and with people having a common scientific language, we don't, there's national tendencies. There's things that people there's aspects of mathematics that you just think, well, that never would have been thought of in that country. So in that sense, it's a very human activity, and it depends on, I don't know, accidents of history, perhaps some cultural things. I don't. It's a little hard to know exactly where those things come from, but I think there's some actual differences in that humans add something to this in a way.
Do you believe that mathematics is intrinsically related to our physical universe, or would mathematics exist independently of it?
I don't really see anything existing outside of our universe. I mean, that's isn't that? I mean, it's almost sort of the definition of the universe to me. I mean, I remember hearing this, seeing some sort of joke physics exam, which, in theoretical physics, which said, define the universe, give two examples. I mean, there is the universe, and that's what. And so in a pedantic way, the answer is, of course, no. Um, that it can't exist outside of the universe. In a But in a human way, I mean, it's there are certainly mathematical structures that you're not going to see, or that you don't necessarily see in the physical universe, that exist only in our minds. There's certainly lots of, I mean, it's not at all clear to me that you see, I don't know, as we study in mathematics, spaces with infinite dimensions and so on. They arise by considering or measuring, thinking about the potentials for measuring all sorts of things in the physical world. But whether those whether those as mathematical objects physically exist someplace, that I don't know. Numbers certainly exist, because again, you can look up at the stars and start counting them, or you can look at whatever, whatever Archimedes did and try to count grains of sand. I mean, you can count things that physically exist. So numbers exist, and all those consequences of numbers then have consequences that stem from the physical world. But I don't know that the actual mathematical objects that we dream up and we, define by axiom systems, really exist.
Now, how would you define the concept of a number, not referring to any physical object in our world? Because it is very simple for teachers or for whoever to define numbers as look, start counting apples, and when you reach the number of two apples, then you have known that you have reached the number two. That representation of that amount of apple is the number two. But that is sort of an internal explanation of the number two that makes use of physical objects. Is there, I'm asking you whether there is even an explanation for how numbers can be defined without touching anything that is physical.
Well, I mean, this is not really my strength, but as a student, you study axioms of set theory. I think we all learned whatever Zermelo-Fraenkel, I think is what it's usually referred to, with choice. I think is somehow the version that one learns, and certainly in a U.S. graduate school, and certainly in one that's not particularly concerned with foundations. Um, and those things start with you start with the empty set. So I could turn the question back around to you and say, well, can you define the empty set without reference to the physical world? And well, that one seems easy because there's nothing there. So, or can you define the notion of, the primitive notion is not the notion of number, actually, in the oldest axiom, or in the most common axioms for number systems. It's the number of set, it's the concept of set, and it's the concept of inclusion and the operations that we do with sets. And once you grant those, then it's perfectly sensible to define the number zero as the cardinality, say, of the empty set, and then the number one as the cardinality, which you, again, as a concept you have to define, but as the number that's associated to the set containing the empty set, and so on. This is what we learn, and so in that sense, it doesn't have it's a little artificial because you could say, well, this was a struggle, I think, in European mathematics till fairly late in history, or fairly recent, from a historical point of view, times, whether the empty set had an independent reality, or whether the number zero, put a different way, the number zero has an independent reality. So could you define it as the absence of things? In some sense, that's a perfectly fine definition. Um, it does in some way have a reference to the physical world. You think, well, what's an example of nothing? Well, space with no rocks or particles or light rays going through it. That would be empty space. So that's a vacuum. And so that's somehow uh, our model for the empty set. So I don't know. I think I've sort of talked my way around in a circle here. I've started by saying, well, you start with the empty set and build or the number, and build the number zero, and then it's not so hard to build the number one. But I suppose you could argue that's still based in some physical reality. The answer is, of course, we don't know, and I certainly don't know.
How can it be that mathematics is so well and accurate in describing our physical reality, and that the laws of nature have been tested to follow mathematical truths, mathematical laws so accurately and so deeply far into the structure governing our physical reality? How can it be?
Well, I mean, I think the answer to that is that we don't really know that that's true. And I don't mean we need more decimal points in our calculations of the subatomic particles and so on, because that is truly remarkable accuracy that theoretical physics can predict. But what you said about the close modeling between mathematical ideas and the physical world is true in some domains. It's certainly true in the domain of physics, in the sense of even the oldest ideas, Galileo, that a ball or an object traveling through the air would travel in a parabolic arc. I mean, that's um, and with its explanation by deeper explanation by Newton, that's a remarkable thing. But we don't have anything close to that kind of fundamental principle, I think, related to a huge amount of the rest of what I think of as the domain of science, which includes life and biochemistry and biology. There's all sorts of stuff that's wildly inaccurate in its understanding, and I think really has no true mathematical model. So I don't know that it's actually true that we are able to describe the physical world, because I think life, and certainly on this planet, it's not describable, and it's not currently describable in mathematical terms, despite the efforts of many brilliant people, and despite many interesting things that can be said. So first off, I think I think the premise of the question is not quite correct. That is to say, we can't really, mathematics. You can't just put the whole thing in a big machine at this point. That said, I mean, but you could limit the question, and maybe this is what you were trying to ask, which is why is the world of physics and particles and so on, why is that so well modeled, or why is some part of it modeled? Well, part of it is that is a sort of a circular argument, which is that a lot of mathematics grew up precisely with the goal of finding a model for all of that. So the ideas of calculus are, in Newton's treatment, completely tied up in his quest to understand the basic laws of motion and of gravity. Now, actually, I I've not read it myself, but I've read that if you read Newton's Principia Mathematica, that you'll find that when he proves things, it's about, say, the fact that orbits are elliptic or lie in a plane, that he actually disdained his own tool of calculus and used the Euclidean geometry. But one can go back and redo all that. And so the amazing part to me is that that's an amazing accomplishment, and I think one of the great feats of all human thinking. I mean, it's even how many centuries later, it's still quite amazing that you can write down a mathematical description of or you can write down mathematical equations that govern how the planets move and all the other bodies. Now that as the mathematicians of the 18th and 19th, and well, I mean, since the 18th century discovered, that's not good enough to actually fully describe things. We still don't know the full solution of many body problems, even 2 or 3 body problems of things flying around out in space with obeying the simplest of laws. That's not understood completely. So, but in any case, the description is correct, and it's in some sense deterministic, although as Poincaré showed us, it's not truly deterministic. The laws of motion. So, anyways, what's really striking is that the laws of physics that were conceived of in this sort of macroscopic setting to try to understand the movements of the planets and stars and so on would actually have any application to things at the smallest of scales of atomic particles and subatomic particles. It's the same mathematics. I mean, it's a little more complicated when it comes to electricity and magnetism, and a lot more complicated when it comes to quantum physics. But to me, the fact that it's prevalent at such vastly differing scales and with vastly differing forces and so on at work, that to me is the most remarkable part of the whole thing. That the calculus that Newton and Leibniz invented has anything to say about this vast number of domains that they were unable to even conceive of in a realistic way. So I sort of forgotten your original question. You're asking why is that true?
A lot of the unreasonable effectiveness of mathematics. Yeah, why?
Yeah, well, I don't think I think I don't think it's unreasonable that the calculus and so on would be extremely effective in describing the motions of of things in the large. I think what's astonishing is that those same laws of physics, or that some of the laws of physics can be expressed in the same terms. The reason I don't think it's unreasonable on large scales because those were the terms that were invented precisely to describe those things. What's amazing is how effective it has been in many other domains, but not in all domains. And because you can't, despite the fact that we give our students these sort of fake problems to solve about biological systems and ecology and so on, predator-prey systems, which we teach our students even in first-year calculus classes. Those things are effective in saying something, but they don't truly reflect at a fine scale, even at a moderately fine scale. They don't reflect the actual goings on of life and what happens out in the world. So I think that's quite a puzzle, and it's a challenge to mathematics now to find new tools that give something approximating the kind of accuracy that the physicists are able to get. The other thing I would say is again, this is as an outsider from physics, is that physicists, and I gather this is your background as well, have a different relation to mathematics than mathematicians do, which is to say, we say, okay, here's our mathematical structure, and let's see what we can do, maybe build new structures that would accommodate what seem to be the observed laws of physics. physicists are much more sanguine about adapting mathematical ideas. They're just going to take those techniques and say, okay, well, that didn't quite work, but we'll change this, we'll change that, and they fine tune the mathematics as they fine tune. Again, this is my observation from the outside. They fine tune the mathematics as they fine tune the mathematical models, and there's lots of things that lots of very precise numbers that seem to come out of taking, in I don't know, fancy versions of quantum physics and quantum field theory that where you calculate things by making all sorts of unrealistic assumptions, or not maybe not unrealistic, but unproved assumptions about the way things work and approximations and just kind of canceling things that look like they're going to give you infinity in some integral and so on. And so I don't know, is that and then they sort of work on their mathematical models and so on, and then they produce these numbers that are then reflected in experiments. But that's not what mathematicians, I mean, I don't think a mathematician would be capable of doing that. I think that's just sort of where we get off the bus. I think when that sort of stuff starts happening. So I don't know. I mean, I'm not sure I am quite sure what the theoretical physicists are doing to produce numbers that could be tested by experiment. It does not. It's not mathematics. Whatever it is, it's not mathematics in my sense. So I don't. It's a little hard for me to. So I think it's unreasonable, and it's an unreasonable use of mathematics, but not unreasonable. But it is also quite effective. So I'm not quite so I sort of separate the concepts in some sense.
Do you think there is a mathematical explanation for every physical process that we experience in this reality? For example, you mentioned that we don't have the mathematics to explain the emergence of life. We also don't have the mathematics to explain what we humans call the experience of being conscious, the experience of consciousness, and probably many other processes related to ourselves, human beings. Do you think that these stages or these domains are simply at early stage in their mathematical development, and that eventually there is a mathematical explanation for these processes, or perhaps there might be physical processes devoid of a mathematical explanation?
I think I don't know whether we will. I don't find a philosophical objection to the idea that there's a mathematical or even physical basis for consciousness. I mean, some people might dispute your premise. They might say, well, consciousness is not a physical thing. My view is that, well, of course it is. If you get hit by a truck and die, then you're no longer conscious. Or at least as far as anybody knows, you're no longer conscious. I mean, so there's something physical that, I mean, there was something physical that happened to you when you got hit by that truck, and then your consciousness disappears. And it's you have only to witness, to be more somber about it, a relative or somebody passing away, and passing from consciousness to unconsciousness to being dead, to say, well, something actually happened. And you can't really tell the opposite of, it can be at a birth, but who knows when consciousness actually started there. But death teaches us that, at least to me, teaches me that consciousness ends and it's tied to something physical. So in that sense, I agree with. I guess I'm saying I agree with your premise that even things that are more than somewhat, that are completely mysterious to us, as in the nature of consciousness, I think my belief is that they have a physical basis. And in that sense, well, there's a reductionist view of biology, that, biology is at some level chemical processes going on in physical and chemical processes going on in the body, and all those things are governed ultimately by laws of quantum mechanics, and so therefore in principle it's amenable to mathematical analysis. Will we ever get there? Not for a very long time. I mean, even I mean, chemists, one of the experience, an experience, sorry for the little digression, but when I was in graduate school, my roommate was not a mathematician, but someone studying physical chemistry. Now, physical chemistry, as the name suggests, as close to as close to physics as you get. So he was studying quantum mechanics because that's at the heart of all of the things that they do. But they didn't analyze things mathematically. They did experiments, and then they took sort of higher principles that were could be discussed a little bit in terms of the mathematics of quantum physics, and just calculated with it. So I don't know. It's not this sort of reductionist view which people have, which conveniently puts mathematics at the very pinnacle of the whole operation. I don't believe that that's possible to actually think that way. People who do, because the great discoveries throughout the world of physics and chemistry and biochemistry and the life sciences, those are all done without they're all done without this reductionist view of things. So in the end, I think there's philosophically, sure, there might be some kind of mathematical explanation. I don't think we'll find it because I don't think it's actually important to find it in that sense. In other words, to reduce it to the things that we know now. On the other hand, there's other things in the physical world. So you mentioned consciousness. The other one I think that's very or another one that's extremely tricky is the idea of language and human communication, because those are physical things in some sense. We sit there and we talk to each other. Ideas get passed along, or emotions or facts or what have you get passed along. And I would have said, 10 years ago, well, that's an intrinsically human process. But now you see all this stuff, artificial intelligence and chat GPT and so on, which none of which I understand particularly well. And it's at some level, those are very mathematical things. Now, it's not somehow the mathematics of calculus, it's the mathematics of probability and statistics and statistical analysis of language and so on. And I don't think that constitutes actual language. So I don't think I don't think language has not been solved in a sense, but language has been imitated successfully enough that you can almost say that it's been recreated in a mathematical way. But I don't think that really answers your question, because you can sort of make something that looks like it's an analysis, but it really is not.
So basically, I say we could delve in a bit into your research, maybe.
Sure, that would be fine.
Now, what is topology, and particularly low-dimensional topology?
Well, topology, in the very broadest sense, is a way of thinking geometrically about things without involving distance. Now, that's of course a complete contradiction in terms, because geometry, by its original name, which refers to measuring things, is of course something that's concerned with distances and so on. But the question is, what remains of geometry when you don't worry too much about the actual lengths of things and you worry more about their shape. So, for instance, in plane geometry, we of course learn the difference between, or the relation of congruent triangles, which is the one that's really most um, tied to measurement. Triangles are congruent if their sides are of the same length in the corresponding order. And we learn some things about that. For instance, that if one triangle is congruent to another, and the second one's congruent to a third, then the first and third are congruent. So these are things you learn whenever you learn plane geometry. But then it's kind of interesting. So one of the things you observe is that, well, congruent triangles have the same angles. So and we say they're similar, which is a sort of a weaker word. And then you realize, well, there are triangles that are similar to each other, because you could take a given triangle and just rescale it. and you learn something fundamental. There are some interesting things that you learn um, that you can still deduce lots of properties of triangles from knowing that they're similar. For instance, you would know not you wouldn't know the lengths of the sides, but you would know the ratios of lengths of their sides, or you would know something about the ratio of lengths of perpendicular bisectors, or various things like that. So we what is so technically what have we done by passing from congruence to similarity is we've loosened the equivalence that we think of between um, triangles. Well, but you could say, well, a triangle and say a pentagon have well they're not the same. They can't be similar because one has more angles. They can't be congruent because one has more sides, and it doesn't make any sense. But still, one goes around and the other goes around, and you have a series of sides that don't intersect and join up. So in some sense, well, they're rather similar um, objects, not in the sense of angles. Or you could say, well, the same thing is true about a circle. It has some properties in common with a triangle or a pentagon or however many sided polygon. So you could ask yourself, well, what do all these things have in common with each other? Or if you, in fact, if you had a circle that wasn't necessarily nice and perfect and round, but looked more like a rubber band, was sort of distorted in some way. Well, all those things are so if you look at them, they're clearly have some quality in common. So the way you define topology is you say it's the study of properties that that objects might have in common. So now, technically, what does it really mean? Why is a triangle this? What? How do you see that a triangle and a circle, say, have something in common? Well, you could imagine inscribing the triangle inside the circle. So just imagine you have a circle and pick 3 points and connect them by lines, and you have a triangle. And now just sort of stand inside and blow, like you were inflating something, and then the sides of the triangle would be pushed out onto the circle. So what is that? What have I done? Well, I've really made a function. So a function is an assignment of values of one object to another that goes, in this case, from the triangle to the circle. And it has the nice property that it's continuous. We didn't break or have any disruptions in that. In other words, or nearby points went to nearby points. Now that's something that's said in terms of a measurement, but can be said without the measurement. And then there's a reverse of that. There's an inverse of that function. If you imagine taking the triangle and kind of shrinking it, I guess we could say shrink wrap, and just kind of shrinking it down take the circle and shrinking it down onto the triangle. That's kind of an inverse of that process. And again, that's continuous. So topology said in its broadest term is the study of objects where you allow the equivalence between them to be some notion of functions and their inverses that have this continuity. Now, I've completely stepped around the question because I didn't tell you what an object was. Well, that gets a little technical, and I probably wouldn't go into it. But for instance, if you know how to measure distance, if you have some set of things and you know how to measure distances, then you can impose that measurement system and use that to define continuity. That's something we learn in school. So that's one very common class of topological objects, is sets that have some notion of distance function. But you can be a little more general, and it's one of the things that was understood in the late 19th century and early 20th century was how to say all that without explicit reference to the measurement of distance. So that's the field of topology. These days, the way I've described it, it's a very general subject, and it's foundational. A huge amount of mathematics is said in those terms, and it is an active field of research. But to me, you get to ask much more interesting questions if you are a little more restrictive in the kinds of sets that you look at. So, and this follows, again, the great traditions that came out of all sorts of other bits of mathematics from the 19th century, what many people would say is the most interesting. You say, well, and so here's an example of a set that in which you can study topology, which would be the Euclidean space. So the line, one-dimensional, plane, two-dimensional, solid Euclidean three-space, three-dimensional. And in a more abstract way, you can choose any number of coordinates and define a notion of distance using those coordinates. And then you can talk about continuity and so on. And then, so okay, that's quite fascinating in and of itself. I mean, it's a highly non-trivial thing to prove that the dimension that I referred to, which in terms of the number of coordinates, that's something that you can't change by this kind of topological equivalence. Things that are topologically equivalent, or as we say, homeomorphic, have different dimensions. So those were early concerns. Again, that's things that were discovered in the late 19th century, is how to even phrase notions of dimension that corresponded to our idea of counting coordinates. But the more exciting thing is then you say, well, um, let's imagine spaces that are not necessarily themselves Euclidean spaces, but locally, that is to say, inside of a small region, look like a Euclidean space. So we do this all the time. And we live on the Earth, or we live on the surface of the Earth mostly. And if you were to look out the window, you would see it looks at least the ground looks pretty two-dimensional. It looks a lot like it's part of a plane. If you lived in a big city, like if you lived in Manhattan, you would even see a grid on if you were looking from a little distance up, or you had a nice one of those nice tall apartment buildings. You see a nice rectangular grid, and well, there you'd even see the coordinates kind of handed to you. I mean, I grew up in New York, so that comes
Hmm.
um, that analogy comes to mind. But we know full well we don't actually live on the surface of a plane. We live on the surface of a sphere. So a sphere, the surface of a sphere, or the so for me, the sphere is actually the surface. If we were to take the full Earth, including the core and everything inside, that I would call it the ball. But the sphere itself is an example, maybe our first example of a two-dimensional manifold. So manifold is just a term that's just, I think the original notion was something many directions, or, as in the way it would be, in religion, manifold wonders or something like that, so many, something you can count. And two-dimensional because it looks like our model of something two-dimensional. So in topology, we study, well, not many people would say that the most interesting kinds of objects to study are manifolds. And having observed that the sphere is two-dimensional just by looking at it, or you can, if you write down a mathematical definition of a sphere, you can certainly find, not on the whole sphere, but on a portion of it, you can find coordinates, as we did, or if you like an equivalent, a local equivalence to the Euclidean plane. We realize that the sphere is an interesting two-dimensional manifold, and it's not the same as the full plane. It has many different properties that are different. So topology is in some sense, could say, or so some version of topology, though the part that I like, has a lot to do with the classification of spaces that are locally like some Euclidean space. So, well, okay, in particular, because of the proofs that were given in the early 20th century about the invariance of the topological invariance of the idea of dimension, we could talk about the dimension of such a manifold. So in other words, if you're on a sphere, then near my house, it looks like a plane. Near wherever you are, it looks like a plane, and so on. So the dimension is sort of a well-defined concept.
What is the notion of a smooth or differentiable manifold? Because when I encounter articles or explanation regarding topology, they always mention indeed that manifolds are the principal objects of study. However, they also point out that the manifolds we are interested in are smooth manifold. So why is that we require a smooth structure on a manifold, and what is even a smooth structure on a manifold?
Okay, so let me answer the why before I answer the what, because I think that's historically correct. And there's really two answers. So the first answer is sort of historical and goes back in some sense to Poincaré. So Poincaré did not define a manifold. I think the first definition or the first attempted definition was Riemann in his famous dissertation from 1851 or 52, something like this, done at the request of Gauss, who was old and had these ideas and wanted to see what some young guy could do with it. But so the original, so Poincaré's actually defined some, instead of thinking about smooth manifolds, he talked about he wanted to have some additional local structure because, as it turns out, it's very difficult. This idea of, so I describe this topological equivalence. Let me use the technical word, which is homeomorphism. It just means the kind of continuous equivalence uh, between topological objects. And to say anything useful or to try to, I mean, so one of the things that Poincaré wanted to do was to try to find tools to distinguish between um, manifolds to show that they were not homeomorphic. In other words, there was no such homeomorphism. And he didn't really know how to do that. So he said, well, let's give it some extra structure. And so what Poincaré did was not actually what's called smooth manifolds. It's closer to what now would be called piecewise linear manifolds. So the Euclidean space has many additional aspects to it. I mentioned coordinates, but it also has kind of a linear structure. There's a well-defined notion of a straight line or a plane or various things like that, sort of linear subspaces. And so Poincaré defined manifolds as being locally homeomorphic to Euclidean space, but able to be cut up into polyhedra. So if you were thinking about something three-dimensional, maybe you would think, or two-dimensional, you might think of it just cut up into actual triangles. So by this, I mean the triangle and its interior. So, and just gluing those together like you would glue together pieces of a puzzle. And you can imagine the same thing in dimension three, where the pieces are now, well, they could be cubes or they could be, most commonly, just for technical reasons, it's very convenient to take tetrahedra, so 4 points, four triangular sides, um, and so on. And that was really an idea of convenience. So that was, and then of course the concern was, well, why do all the things that Poincaré defined in terms of the triangulation, why are those actually uh, are those the same if you have merely homeomorphic manifolds? Because of course you can have a equivalence, a homeomorphism equivalence even from Euclidean space that distorts things. That, for instance, the things I was describing with the triangles and circles, those are not linear maps. I mean, I mean, the one I described takes an arc, a chord, a straight line to a curved arc. So that's not a linear kind of map at all. That distorts linearity. So that was one thing, and so it was understood actually in the so that's one motivation. The second motivation is that you might like to do some other, you might like actually to study things about your manifold. So this really goes back more to the tradition of Riemann, who was interested in, among other things, in sorting out a an idea that was very powerful, that was known much earlier. It was known to Euler, who was at least 100 years earlier, of of complex valued functions that were multi-valued. So complex numbers are if you draw the usual picture of them, really, we could think of them as living in the plane, where sort of one coordinate is traditionally designated the real coordinate, and the other is that sort of typically drawn vertically is the imaginary coordinate. And you can talk about calculus and so on with complex numbers. And it was realized very early on that this was a very powerful idea. Well, so there's this idea of multi-valued functions, like the square root is not, I mean, as we all know, when we solve the quadratic formula, there's some point where, what's a quadratic equation, you come to some point where you say a plus or minus something or other, the square root of something, and it's because of the ambiguity in the sign of the square root. So that the square root is an example of a multi-valued function, which is a very poorly defined concept. So Riemann had a beautiful geometric idea of how to do that using topological ideas. I mean, this is all in retrospect. He didn't quite have the language for it. So in the end, what you're really trying to do there is you're trying to do calculus or algebra and calculus, not so much using the plane itself, but using some kind of interesting topological space that you cook up with. Now the one I'm describing is now called a Riemann surface. And so you want to be able to discuss sensible things that we talk about in calculus. You want to talk about differentiability or tangent vectors and curvature and all the first and second derivatives, all those things that we learn in calculus. We want to be able to say those things. And one of the things you learn, one of the things you observe very quickly is that the notions of calculus are very local. In other words, if I have a function and I want to compute its derivative, I don't need to know the whole graph of that function. I just need to know how that function is behaving right near a point. I mean, that's the definition of the derivative. You vary the position a little bit, you can see how much the function changes, and then you compute a ratio of those things, and then you ask how that behaves when the variation becomes very small. And likewise, tangent lines, and if you had more variables, tangent planes, and so on, those things are defined intrinsically locally. Well, if you think about that, that fits right into it's right in the wheelhouse of topology, because we now have a language where we can talk about things being local. But then you come to a very interesting point, which is to say, well, suppose I have a manifold, so a surface of a sphere, or some other more complicated surface, or maybe more dimensions. And I say, well, I can pick some coordinates. In other words, I pick this near each point, and I have a function, and I want to discuss whether that function is differentiable, and then I want to understand its rate of change, or maybe I want to understand something about tangent vectors. Well, there's an obvious thing to do, which is to say, well, let's pick coordinates near that point, and that is to say, identify it with some Euclidean space, transport my function over to Euclidean space, compute everything in the traditional way, and then just say that that's the answer. Well, that's great, except suppose, here we are separated by 3,000 miles. So suppose I decide to do that calculation using one set of coordinates, in other words, one identification with Euclidean space, and you decide to do something completely different because you have a different view of things, and you do it with some other coordinates. How do we know we get the same answer? What does it even mean to say? How do we even compare the answers? How do I know? So let's even ask the simplest question. How do I know that a function that I declare to be differentiable, in other words, to have a derivative, that you would decide that same function also had a derivative? You're computing it in principle some completely different way. So that's the need. That's the global question that gets very naturally asked. And the answer, again, it doesn't, I mean, Riemann sort of said this, but he didn't have the language to say it. That what we really have to do is agree on the description of our surface or our sphere. And so what does agree mean? Well, that means we really should just choose, we should agree on, we should have, when we say, okay, we're talking about the same sphere, we should not allow arbitrary, or we're not going to allow arbitrary identifications of small portions with Euclidean space, we're gonna sort of agree on a list. Now it's going to be a huge list because there we are allowed to do all sorts of of things, but we have to agree somehow on a list, and the language is very picturesque here because we so each of these local identifications is called a chart. So just as in sailing or navigation or maps or something like this. And then what we have to agree on is and they have to have the property that if I make my identification with the Euclidean space, you make your identification with the Euclidean space, then if I sort of, well, I can sort of go backwards. I can start from my Euclidean space, go to my manifold, and now you take it over to your Euclidean space. Well, that's an ordinary function from Euclidean space to Euclidean space where the notions of calculus are perfectly sensible. So we can talk about whether that function itself is differentiable. We could talk about whether the inverse, if we did the inverse process, if that's differentiable. And we can even discuss in some notion what its derivative is. So the technical definition is, I mean, I've come very close to the actual definition, which of a differentiable manifold. It's a collection of charts, that is to say, and an agreement and a restriction that we're only going to consider ones charts where the sort of overlaps are differentiable in the traditional sense. So we're going to although that's very large because there are lots and lots of differentiable functions in the world, and you can always just sort of change things. But that's the idea of a differentiable manifold. So you can maybe to summarize it, it's a mapping out of my space together with an agreement that we're only going to use certain kind of nice maps. And what's the niceness property is that they are compatible with each other. So at that point, we've achieved something great, which is we now know how to actually discuss the basic ideas of calculus. So that's the motivation. And as it turns out, that also achieves Poincaré's goal because that also provides us with enough local structure that we can start to calculate the kinds of notions that Poincaré handed to us of what's called algebraic topology. So anyway, that's a long answer, but it's a hard question.
Now, low-dimensional topology is involved with the study of three and four-dimensional manifolds. And low-dimensional topology is the main research area of your work, right?
Right.
I would like to ask you, what is special about the third and fourth dimension? Why did you pick three and four manifolds and not seven and eight manifolds? And which of the two is more complicated working with?
There's a lot of history to all that. Um, you can ask the questions you can ask, the initial questions you ask, how do you find all of the manifolds? How do you distinguish them? Can, of course, be asked in any dimension. The answers in dimension. So maybe I should slightly correct you, which is to say, um, there's still a lot of interesting things to ask about one-dimensional manifolds. That's maybe a surprising thing. That's not so. I mean, if in terms of classifying them, there's not so many things to say. If you impose some simple hypothesis, maybe that it should be only in one piece connected, then there's really not so many choices. There's a circle or a line, or if you allow it to have an endpoint, it could be a ray or an interval or something like this. But there's still interesting questions from topology of one-dimensional manifolds. So I don't want to dismiss all that. And the same thing for two-dimensional manifolds. And again, this goes back to Riemann. Again, if you make some simple hypotheses, you can say what all the surfaces are. So in terms of just the simplest question of just, well, how many manifolds are there? You can write them all down. You can give a concrete description. On the other hand, there's still, again, this many, and this study of surfaces in that sense is quite active. even though classifying surfaces is maybe not, was done, not quite 200 years ago, but somewhere around 150 years. Anyway, quite a long time ago. But paradoxically, higher dimensions were understood quite well. And there's reasons for that. And if you want, I can explain what those reasons are. But dimensions, well, 5 dimensions is sort of borderline, but dimensions of six and manifolds of dimensions 6, 7, and so on are are they're not completely classified, but in some ways, what you do is you reduce them to questions, to other kinds of questions from maybe some other domain of mathematics, and those questions are either interesting. What historically happened was in the decade of the I would say the decades of the 50s and 60s and continuing into to the 70s, that was so well studied and they did such a good job that the questions that they were left with were just too hard, rather technical, and those fields are still with us, and they're still they actually in some ways had a renewal of energy in the last say 10 years. But so when I came into math, it came of age in the late 70s, the feeling was, well, a higher dimensional topology was now understood, and there was great mysteries in dimension 3 and dimension 4. They're really quite different qualitatively in terms of this sort of theory. Dimension 3 was completely transformed, which well, first off, it was understood right away that there were many special properties. For instance, if you disregarded the hardest problem at the time, which was the Poincare conjecture, which was supposed to ask what was the characterization of the three-dimensional sphere. In other words, how can you tell by computing one thing whether or not you've got the three-dimensional sphere? If you somehow disregard that, which they artfully managed to do in the 60s, there was essentially an algorithmic classification, or close to that, for large categories of three-dimensional manifolds. Is impractical, but sort of there, and that was the nature of things. It was very combinatorial. It used this idea that I referred to earlier from Poincare of cutting things up into three-dimensional simplices and then just asking how they fit together. And since the boundaries of those three-dimensional simplices, the way that they're glued together, were two-dimensional, those maybe you could sort of say, well, it's all reduced to somehow combinatorial ideas. But Thurston had this remarkable insight that, in fact, there was something deeper going on. And he began to explore the geometry, now in the sense of the original sense of measuring things. And he discovered that, he and others discovered that most three-dimensional manifolds had a sort of deeper geometric structure, where, in other words, they had a way of measuring distances called a hyperbolic metric that was actually contained vast amounts of information about topology. Now, this is not completely unprecedented. You can say the same thing about surfaces. Surfaces, two-dimensional surfaces, are understood very well. There's a very close relationship between geometry, particularly hyperbolic geometry, and the topological side of surfaces. Again, this goes back to the beginning. This is really something that Riemann understood in his exploration of, or started to understand in his exploration of complex variables. But the fact that you could do this in dimension 3 was a complete shock, and it really transformed the field. So when I was a student, that was one of the things I studied, because it just seemed really interesting. That you could do that seemed completely unlikely. Thurston brought all sorts of classical techniques from the study, from Riemann's study, and things that had been developed in the subsequent century to that. So So that was already very different. That was really different. That was totally different from what had gone on in high dimensions. Dimension four was a complete was an even bigger mystery. Um, so I was a student in Berkeley, and my advisor was Rob Kirby, who had been somewhat had been played a major role in the classification of high dimensional manifolds. Had felt was along with other like-minded people that they recognized, and if you like, I could describe why, but they recognized that the techniques that worked in higher dimensions you just didn't know how to get even started with those arguments. There wasn't enough room, as we said, to get started with those arguments, and something seemed different. So they started drawing pictures and truly representative pictures of four-dimensional manifolds, slightly complicated ones, and manipulating them, trying to see, well, can we find homeomorphisms or I didn't define it, but diffeomorphisms, which means the kind of equivalence that you get in the world of differentiable manifolds, where you require that the functions going back and forth be differentiable, as we now, as I was describing, we now know how to even give sensible meaning to that. So they were drawing pictures. They just could, and you could learn a tremendous amount. You could learn a lot about the structure of an individual manifold. You could start with equations, polynomials, and get yourself remarkable pictures just out of this. It was a very empirical subject, but there wasn't a theory. And then, as I finished graduate school, two remarkable things happened within months of each other. One was the work of Friedman, who took a program to extend some of the high dimensional theory into dimension four. But with the stipulation, it sort of really broke down. It only said something about topology in the original sense, about equivalent, sort of this continuous equivalence. It said nothing about the sort of differentiable equivalence because of sort of technical reasons. There was some passage to a limit that sort of blew apart any notion of differentiability. Very complicated process. So there was that, which was amazing. So he proved the four-dimensional Poincare conjecture in the topological world. In other words, he characterized what a four-dimensional sphere would be by purely in a purely topological sense. And then a few months later, this was followed by the work of Donaldson, who made what's still an astonishing discovery, which is that that well, he proved a specific theorem, but it was grasped immediately by all the experts that meant that there was a very unexpected divergence between the notion of topological equivalence, in other words, what I was describing as homeomorphism, and differentiable equivalence, which I was describing as diffeomorphism in dimension four. That there was just something very different. And it took a while. I mean, these were two giant ideas pointing in rather opposite directions. And so there was all this just to explore. It was as if you were, searching for gold on a mountain, and with a toothbrush and a dustpan, and trying to pick up a few little grains, and then all of a sudden somebody walked in with a drill, and you could all of a sudden see things that you sort of suspected were beneath the surface, but also they were there. And it was an amazing time and an amazing opportunity. So lots of things like, why does this subject develop now, or why did you get interested in these things? It's really opportunity. It took when with Thurston's ideas, it was all of a sudden this new view of three-dimensional manifolds and all these fascinating ideas that he brought in from out of nowhere to do this. And then in dimension four, there was this wealth of tools that we now had.
You said that some of the people that you mentioned before were trying to make images, picture,
Yeah.
manifolds about the fourth dimension. Can I ask you, how do you develop intuition for the fourth dimensions and four-dimensional manifolds? Do you even try to picture them in your three-dimensional mind, or do you just forget about imaging and picturing and you just wait, or at least you just let the math lead you and guide you?
Well, of course, you can't draw a full picture. Um, I mean, the fact is, you can't even draw a full picture of a sort of global three-dimensional object in three-dimensional space. You can't, I mean, in fact, you can't even, I mean, so we're here we are, we're in three-dimensional space. So our tools for visualization are somehow limited to what we have. But even there, let me point out, our tools are even more limited than you think. Despite to my great regret, we have not invented a three-dimensional blackboard, like that you see on, I don't know, Star Trek or something, where someone waves their hands in the air and you see objects created in just sitting there in out in space. We're 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 uh, we're drawing them on a piece of paper on the blackboard, or maybe these days on a computer or a tablet or something like that. But it's still fundamentally something two-dimensional. So we develop all sorts of codes, and those codes. This maybe goes back to your first question about the is mathematics a product of our imagination, or is it in the physical world? Those codes are completely um, realistic. So maybe I could, well, realistic because we have our brains as the additional tool. So for instance, here's an example. Something that people who are studying three-dimensional objects might consider would be a knot. So you can imagine a knot is an intrinsically, well, it's a circle, say, drawn in three-dimensional space and tied into what conventionally would be called a knot. So an overhand knot, or trefoil knot, or figure eight knot, or something like this, or of course, there's many more complicated ones. Well, how do you draw that? Well, you can get a piece of string and tie the knot and glue the ends together. That's certainly a plausible way of doing things, and people sometimes do that, but that's not so conducive to maneuvering and thinking. What we do is we draw a projection. We imagine that we've actually taken our knot and maybe even shown a light on it and projected it onto a board. Well, if you do that, of course, you lose all sorts of information where you lose the information of which part of the knot is going over which other one. So you just draw it on the blackboard. You put a little indication, you erase a little part to indicate that something is going behind. So that's not a real picture. It's not realistic. I mean, you simply can't do that realistically, but that code tells us exactly how to reconstruct the knot. In other words, if someone came into my office, which has all sorts of knots all over the blackboard, just from whatever I happened to be thinking about the other day, and it would see also a knot, and if they wanted to, they could take a piece of string and draw and make a physical model of it. So it's complete. So in that sense, it's a projection. It's one of your questions you sent me asked about Platonism, but this is literally Plato's concept of something being projected on the wall. It's just that we project it on the wall with with little extra information. We're not losing the information. So that's a simple thing, because that's an object that at least exists in three-dimensional space, and then what we've worked out is how to retain the sort of three-dimensional side of it. But in dimension four, so dimension four, it gets a little hard. There are people who will tell you that they can draw a picture of something that retains some extra information, but those things are hard to do, and for me, very hard to interpret. but there's tricks. You can imagine, so you can imagine, so this is not the way it always works, but if you were working in a four-dimensional manifold, you could, so what would you do? Well, you could imagine that the four-dimensional manifold is sort of like Euclidean, like four-dimensional Euclidean space. You could imagine it as sort of sliced into parallel copies of three-dimensional Euclidean spaces. So again, just go back to ordinary three space. You can think of it as just a series of planes. And we even, you see that as in art all the time. You see something that's been sliced into different levels, and you can imagine in your mind's eye assembling all the different levels. So you can do that in dimension 4 as well. In other words, you can imagine some four-dimensional object as being comprised of a series of three-dimensional objects. So then now we just have to figure out, well, how does that three-dimensional object fit together? So we draw those pictures all the time, those sorts of pictures all the time. But that's not, and those are somehow sometimes just to get an image. But if you're asking how, on a sort of professional level, how do we work, we don't necessarily do that. And so it's a sort of a combination of the two things you asked me. You said, well, do you just let the math do its work, or do you, and so one of the things you learn, and this isn't really so much my own work, but it's part of the pictures I draw in terms of, it's not really a technique I would use, which is that, how do we think about four-dimensional manifolds? Well, we think of them, as it turns out, the key or a key to the whole business, at least on the topological side, is to understand how two-dimensional things sit inside of four-dimensional ones. That was, in some sense, what Donaldson discovered, was a limitation on how certain, could you have certain configurations of two-dimensional surfaces sitting inside there's no no differentiable four manifold that had a certain configuration of two-dimensional surfaces sitting in there. And he discovered that he didn't draw any pictures of that. I don't think that wasn't his style. He discovered that sort of indirectly, but you could interpret it that way. So, but for those of us who are more topologically or geometrically inclined, that's the key. And so instead of trying to visualize some global four-dimensional thing, we might try to answer these questions. And now for surface inside of four-dimensional things, then there's all sorts of geometric techniques, this kind of ideas of slicing things. Well, that's very powerful. That's actually quite an old idea. Because if you imagined a surface in something four-dimensional, and you imagine that you had a way of slicing that four-dimensional thing into three-dimensional ones, well, your surface then gets sliced up into circles in something three-dimensional, and all of a sudden you're back to the pictures of knots. So you could, so there's a whole gang of ways of reinterpreting what turn out to be the fundamental or the most useful techniques to bring them to pictures that we can draw. So that's one answer to your question, which is to say, you don't really take some very complicated four-dimensional manifold and sort of see the whole thing all in one go. What you do is you try to see features and see. So as I say, one of the key features has to do with the way surfaces sit there. The other side of it is a completely different way of thinking about manifolds. And this is the kind of pictures I was alluding to when I was learning how to draw when I was a student in Berkeley, where this technique was really pioneered and advanced by my advisor and the generation of students who were just before me. They said it was a very communal kind of effort. And this one, I think, is best understood if you think of, well, at least for me, it felt a lot like when I was young and I built models, like ships or airplanes or things like that, or these. And so what does that mean? Well, you're given a bunch of standard pieces, you know, they might be shaped a little bit. You know, might recognize it as a part of a wing or a fuselage or, you know, something like this. But you're given these pieces and you're given some instructions about how they glue together. In other words, and so the box comes, it's your birthday, someone hands you a model, you open it up. It's this massive pieces, all of which, you know, are more or less the same. They're bits of plastic and they have numbers on them. And the number, and they had, and you have glue. And then the number, and then you have a plan. And the plan says, oh, like glue this piece to this piece, glue this other piece to this other piece. And, you know, eventually, you know, an airplane takes shape and you can see it and play with it. So in dimension, actually this idea works in any dimension. And there's slight variations as to how it works in dimension 3 and dimension 4. But let's just say for dimension 4, it turns out that I mean, there's some pieces that you can visualize. So the starting point is just something very simple, which is the four-dimensional ball. So the four-dimensional ball, well, again, we can't draw it in three-dimensional space, but we don't care about, in some sense, when you're gluing things, you don't care about the part in the middle, you just care about what happens on the edge. Well, that's the boundary. The edge of the four-dimensional ball is the three-dimensional sphere, and that's something we understand. And everything else in my model kit is going to be glued to that. So the question is, how are they going to get glued? Well, some parts are glued essentially near points. In other words, along sort of. So again, I've sort of forgotten this sort of bulk part, the interior of this ball, this four-dimensional part, and I'm just going to concentrate on the gluing instructions. So there's some pieces that are glued on in a very simple way, and then but then the next most complicated ones, which are really the key ones, are pieces that look so that these pieces look like a two-dimensional disk, but thickened up by a two-dimensional disk. So in other words, it's a Cartesian product of two-dimensional disks. And that's something you can understand very well. We can draw, we can't draw that itself, but we can draw representative pictures and we can certainly reason mathematically about all that. If we wanted, we could put coordinates. There's, you know, one pair of coordinates corresponding to one two-dimensional disk and another pair corresponding to the other. And sometimes we resort to actually describing things in that way. But now, if you take the edge of one of those disks and just keep it thickened up, that's the analog of the edge of my model where things are getting glued. And how's that getting glued onto this three-dimensional boundary of what I had already? Well, it's getting glued along a knot. Well, it's a knot and a little more information. So this is a technical point, which I won't describe, but it sort of describes how the disk twists around as you glue it in. But in any case, it's very precise gluing instructions, just like you would get in your that comes in the box with your model. It's a rule, and it has a mathematical. Well, again, so this goes back to your earlier question. To me, it has a mathematical reality. I mean, you could, in principle, define it by a set of equations somewhere, living someplace, but it doesn't matter. It's an abstract thing. I just say, well, the mathematical object is completely well defined by the gluing instructions. So let's, to some degree, forget the object and just concentrate on the gluing instructions. So what does that mean? That means you've taken, so operationally, that means you have your blackboard, which is where you've somehow visualized your sphere, your three-dimensional sphere. And you have these attaching places and some extra numbers, which are some additional important data, and you just draw them. So what does that mean? You just draw a bunch of knots on the blackboard, maybe grabbing each other and linking each other in some complicated way. And the astonishing theorem, which was just proved in an abstract way, is that information that we just drew on the board. Well, I didn't draw it for you, but we could have drawn on the board. That tells you everything you need to know. In other words, those instructions, so that bunch of knots, which which and those numbers and the way that they grab and link each other, that actually determines the manifold, determines it in its smooth structure. In other words, its differentiable aspects as well. So that's great. That's an amazing achievement because we can now take a very complicated object, maybe something described by, a polynomial equation of high degree with complex numbers and a lot of variables, and that we know for some reason describes a four-dimensional manifold, and we can draw it. We can look for surfaces inside it. We can try to break it up into simpler pieces. We can ask whether you can do those things. So that's a huge achievement to be able to do that. And three-dimensional manifolds have actually a couple of different descriptions of this same sort. Again, ways of drawing things that can live on your blackboard, and another topologist can walk in and immediately say, "Oh, I see. That's the lens space L51 or whatever it is, something described by in some other fashion." And the second part of it is that those instructions are not unique. In other words, I might describe a manifold by one set of instructions, somebody else might describe it by another one. We can put them next to each other on the blackboard. They don't look the same. They might not look the same. But then there's a set of manipulations that you can do. You can sort of imagine sliding the knots around. There's an amazing process of sliding one over the other. You can sort of introduce things that extra little bits of the diagram that don't affect what manifold you have. And eventually you actually prove a theorem that says, well, if those two manifolds, so the first part of the theorem is if you do these operations, then the manifolds you get are diffeomorphic. So that's very nice. So in other words, if you wanted to prove that this one manifold was actually that you drew in a very complicated way with actually something very simple, you could try to do that. So that's hard, but it's doable. And there's a lot of brilliant papers by brilliant people doing that sort of thing. And then there's theorems that say, well, in fact, if they were diffeomorphic, if you knew for some reason that they were diffeomorphic, then you should be able to manipulate the diagrams to go from one to the other. And that's also quite a powerful thing, because then you could say, well, let me try and tell them apart. Let's see if we can calculate something from this diagram, some numerical information or some, I don't know what, some other mathematical, some other kind of maybe algebraic object, calculate it from this diagram, and then I calculate it for mine, you calculate it for yours, and we get different answers, and we conclude that our manifolds can't be diffeomorphic. So that was sort of the state of the art for four-dimensional topology and some parts of three-dimensional topology when I started. What came next, and which fascinated me, was the use of, well, in dimension 3, of geometrical ideas to tell manifolds apart or to uncover their properties by calculating stuff that came from this sort of canonical geometry that Thurston had provided us. So that I was very occupied with that sort of thing for the first number of years of my career. But as time went on, we started to see that the tools that Donaldson had introduced, which was this idea of gauge theory, all of a sudden gave us new tools for calculating or for distinguishing four-dimensional manifolds differentiably that we previously had not had any tools to consider. So I was really captivated by that idea.
Can you explain what are gauge theories and how do they arise in your work?
Sure. Gauge theory is a gift from the world of physics. The story is actually quite interesting because it's also I think one of the most beautiful interchanges between physics and mathematics certainly that I ever saw in my lifetime. I should also say that gauge theory to physicists means something different from what it means to mathematicians. So to me, here's what gauge theory means. So I'm not this is mathematical gauge theory. Uh, Gauge theory is a part of what's called differential geometry. And so differential geometry, maybe I alluded to in passing earlier, is the study of curvature and how objects uh, curve in space. So it's usually you're sort of thinking about the actual physical properties of space. In gauge theory, we're studying a space. So now again, we have the notion of a manifold usually with some auxiliary objects. So those would be um, geometrical objects that are sort of extrinsic to the space or additional data. So I think in physics they would refer to them as fields, so something like an electrical field or magnetic field. So it's not actually part of the space. It's something that's coming from some physical origin that has a mathematical description. And the mathematical description, as was sort of uncovered in the 70s, the mathematical object or the objects that the physicists were looking at, these fields, turned out to be the same as objects that mathematicians interested in differential geometry had been looking at, which are known as connections. So it's, if you like, a system of measurement or comparison of objects from one point in a space to another. So it's actually a fairly complicated idea, the idea of a connection. But a connection is some sort of mathematical object, some collection of functions um, with an interesting transformation rule. They don't quite transform in the way that ordinary functions do. There's a sort of twist to it. And that twist is encompassed in something called the gauge group, which is usually so that group would be something like the group of matrices of maybe 2 by 2 matrices with complex coefficients, or 3 by 3 matrices with certain extra properties and so on. But in physics, they use more complicated and bigger gauge groups. The great case where the gauge group is the circle, I believe, corresponds to the classical Maxwell equations and the description of electromagnetism. So it really is in physics, is a big generalization of electromagnetism to other sorts of fields. And one of the most important, so there's lots of interesting mathematics that's discovered. This was the correspondence between these mathematical ideas had been developed in the 50s and 60s through the 70s, and the physical ideas perhaps slightly more recently. And it's somewhere in the 70s, it was understood that the language that the mathematicians had developed was a very good model for the ideas that the physicists were already using, even to describe, I believe, the standard model and so on in theoretical in physics. And so there was a great reunion, I think, or great joining of forces. And in the late 70s, under the influence of a number of mathematicians. And so that's the idea of a gauge theory, is this that's something that's fundamentally just some differential geometry, but you're looking at these connections that satisfy certain equations that and the language is all very physical. So you're looking for things that minimize. So each connection has a certain notion of energy, and you're looking for things that satisfy laws of physics, like trying to minimize the energy or minimize something like that. And those equations are the even studied in mathematics, are the Yang-Mills equations, or these days we would call it the self-dual Yang-Mills equations. There's a particular specialization of those. And so it's it's on the one hand a bit of geometry. It's got some interesting analysis to it. Um, and the surprise is that it has anything to do with topology. And this was discovered by work of, well, Donaldson, who was building on work of Taubes and Uhlenbeck from the late 70s, who had been studying this sort of the mathematics of this interesting bit of geometry that descended to us from physics. So Donaldson was just saying, well, let's take an arbitrary four-dimensional manifold or not an arbitrary one with some restricted topological properties, and see what what does the structure of these equations look like. And what he explored, the interesting thing about these self-dual Yang-Mills equations, or actually now we study what is called anti-self-dual, which is um, anyway, that's a slight technical difference. When you study these equations, what you find is that there's not a unique solution to these equations. They're rather sophisticated from an analytical point of view, but they have a remarkable property, which is that the set of solutions themselves is something finite dimensional. And what Donaldson showed, and then continued to show in subsequent works, is that the set of solutions themselves would typically form itself another manifold. So you start with, so it's a very surprising idea. You start with something four-dimensional, and the fact that working on a four-dimensional manifold is important for an assortment of reasons. Like, for instance, writing down the actual equations is a bit of linear algebra that's special in dimension 4. You write down these equations. You say, okay, let's study all the solutions. Well, in fact, the set of solutions is itself infinite dimensional, but you say, well, let's only study them up to a certain equivalence. And when you do that, you find that the set of solutions typically forms a space of some finite dimension. And in fact, you can calculate what that dimension is using what's called the Atiyah-Singer index theorem. So that's a point of analysis. And one of Donaldson's singular contributions was to prove that typically you would get that this space that you got was actually itself a differentiable manifold, or if it wasn't, if it had some aspects that weren't differentiable, that happened only on a rather small in rather small regions. And then he thought, well, what does that manifold actually look like? And when you explore aspects of that, sorry, let me just define it. That set of solutions is what's called a moduli space. So this again is an old idea. It goes back to Riemann, who studied moduli spaces for other sorts of equations and proved that they were finite dimensional, or let's argued that they were, and calculated the dimension. And but here we were starting with something, a four-dimensional manifold, and then you got this moduli space, and then you could explore properties of the moduli space. So to mathematicians, or to mathematicians like me, that's gauge theory. It's this process of starting with something, a four-dimensional manifold. You need to choose some auxiliary data about your four-dimensional manifold. Particularly, you need to choose a system of measurement so we can write down these equations. But once you do that, you write down these anti-self-dual Yang-Mills equations. In theory, well, although in practice it's difficult, you could imagine solving them and finding all the solutions which form a manifold, another manifold, this moduli space, and then you study properties of the moduli space. And the amazing thing is that the properties of the moduli space can be translated back into properties of the original four-dimensional manifold that you started with. So that's gauge theory, at least in the topology world. Now, I don't think that's what the physicists. I mean, the physicists, I think, were very pleased by this development, but they didn't did it. They thought of it in different ways, and they went on to different concerns. But that's gauge theory for us.
What is the most remarkable fact and idea in gauge theory?
Well, I think the fact that it works at all is remarkable. I mean, for instance, Donaldson, uh, this was his PhD thesis, was doing this, and he was looking at said, okay, well, let's make an assumption, which makes some of the analysis a little bit more straightforward, although it complicates some of the analysis also, which is a property of the four-dimensional manifold, an algebraic property that we call being definite. So let's ignore without saying what that means. And he found that if you had something that was definite, then the moduli space was could be written as the boundary of something. Or sorry, then your original manifold could be written as the boundary of something in a way that in fact your original manifold appeared as the boundary of this moduli space. And in some cases, that could prove that you couldn't that you could prove that that just simply couldn't happen. And so that's what Donaldson proved. He said, well, he took it back actually to his office mates, and he said, well, I seem to have proved that there's no four manifolds of a certain kind. Is that interesting? And fortunately his office mates were one of them was Mike Hopkins, who knew enough topology to say, yeah, that's an amazing fact. And so I still think I don't think I will ever surpass in my life the amazing surprise of hearing that argument and hearing so it's not just I mean the fact that, it was a great theorem. It was a big surprise that anybody could prove anything, but the actual argument was so completely out of my realm of experience. You just would never have thought of such a thing, but here this guy did. So I don't know. The sense of the thrill of that was that was a huge surprise, and I don't think nobody expected it, and in historic, with complete revisionist eyes, you can see, well, it's natural how one might have come to that, but even so, the surprise was really overwhelming. And for me, it's not that I can't say I just dropped everything and said, well, I'm going to work on that, because I didn't. First of all, I didn't know how to work on that. I didn't even know the basic ideas. And also, there was a sort of idea at the time said by some various famous mathematicians whose opinions I respected was, well, that argument's so crazy. We'll never prove anything with that again. And then over the next few years, it was clear that we could prove not by that exact argument, but by that same scheme of starting with the manifold, passing to its moduli space, we could start to do incredible things in topology. So that was, I don't know, I still think that's an amazing surprise, and one of the great fortunes of my life to have been there when that happened.
You previously mentioned that knots are related to your research and to manifolds. I would like to ask you, or let's say, how do knots appear naturally when dealing with three and four dimensional manifolds? What does it mean that they appear naturally?
The basic building blocks, or one of the basic techniques for just simply describing manifolds in a topological way, is just you draw knots. And so that's quite interesting in and of itself, as just sort of I don't even only on the art, if only on the artistic level. I mean, you draw these beautiful pictures and manipulate them. And now I actually, despite the fact that I was a student and grew up in that school and know how to do all that, I, I it occurred to me a number of years ago that I had almost never proved any theorem, and I've written a lot of papers. I don't think any of them the actual fundamental step is was achieved by drawing some knots and manipulating them. It's you know maybe it's just that I'm not that good at it, or maybe I like doing other things. So I never did all that. On the other hand, the other side of knot, there's other sides of knot theory that are connected to topology, which is something I've kind of alluded to, but not really said explicitly, which is the idea of invariance. So in other words, you have manifolds and you want to know, can you tell them apart? Well, you could ask the same question about, um, for instance, knots. I draw two maybe different looking knots, and I ask, well, how do I tell them apart? What can I compute? So there's all sorts of interesting things you can ask. So, for instance, one of the great contributions I meant of Thurston, who I mentioned earlier, was to show that um, for a knot, there was a notion that you could study a knot using hyperbolic geometry in a very unexpected way. You you for most knots, he proved that there was a canonical way of making the complement of the knot. So you take the three sphere, you just remove the knot. So that's a three-dimensional manifold, and it has a um, standard measurement of distance, and that standard measurement of distance, this so-called hyperbolic metric, first off, is unique. That's the Mostow rigidity theorem, which was proved actually quite a long time ago, but used from by Thurston or whose importance was repointed out by Thurston. So there's all sorts of interesting invariants you can describe in that way. So you could describe, so for instance, you could just take its volume. In other words, just the way you would take the volume of an object, which depends on local measurements. So, you just imagine cutting it up into little boxes and measuring the sides of each of those boxes and adding them all up. Well, anyways, it turns out for knots, that volume is finite. So I got quite interested in this topological invariant of volume that Thurston had pointed out. So that appeared in my research, and the same thing. There's more sophisticated. Well, not there's other variations on that theme. Where, in other words, where you could say take this hyperbolic metric, compute some kind of differential geometric thing, maybe by an integral, the way you would compute the volume, and see if you can say some interesting things about that. So I got quite interested in how those things behave. There's other interesting properties of knots that are actually connected to four-dimensional topology. And again, this is something that I really enjoy. For knots, you can have there's the equivalence relation that we all would see. In other words, you can turn one into the other just by sort of tangling it up and trying to untangle it, and moving the knot, or basically just playing with string. You could try to do that. So that's a notion of equivalence of knots. But there's weaker equivalences, which are really in some way much harder. So, by the way, the equivalence problem for knots is, again, something that's algorithmic and solved in a pretty effective way. You can put on a computer and decide, for instance, whether or not, if I can draw a very complicated picture, hand it to a computer, and it can bang tell me, well, no, that actually is not a trivial knot, or it could tell me very quickly that it is. But there's other relations. In other words, you could ask whether you could pass from one knot to another in a sort of four-dimensional way. So technically that's called concordance, where you allow the knot to move around in some fashion that's a little bit looser. That turns out to be, first off, an interesting problem in its own right, but it also is tied up in fundamental ways with four-dimensional topology. So one of the things I've enjoyed most is applying ideas of gauge theory to those problems about knot concordance. So it shows up. So these things show up all the time. I mean, there's I don't know, endless collections of great problems that knot theory generates. And that's even though, as I say, in some ways the classification problems are now known to be reduced to algorithms that you can even program in effective ways. But But the problems that are more closely related to four-dimensional manifolds, as it turns out, those are not solved, and they're not at all easy, and they're still quite fascinating.
What is a beautiful or interesting application that not theory and low-dimensional topology have?
How do you mean application?
Well, I mean, if you can sort of utilize the same concepts of low-dimensional topology and not theory in some
Yeah.
other branches of science, for example, in physics or some other biology or anything else that might not be strictly pure mathematics. If there is any, because sometimes
Yeah,
maybe
I don't know.
mathematics
I
is
mean,
also.
there are certainly people who study this. For instance, people, it's actually quite an industry of studying the way that knots appear in nature. So you can find, if you are really diligent, or you can create in the laboratory molecules that are and then that are have long strings. So for instance, various proteins, DNA is the most famous one. And there are in principle, there are interesting ideas of knot theory connected to that. You can have DNA that's, you can draw a DNA molecule that's actually drawn in a knot. Um, there are interesting questions connected to the physical structure of proteins, the way proteins you can in some ways visualize as long strings of molecules joined together. As I say, DNA certainly has that aspect, as we now know. And but in the cell, they don't appear as nice long strings all sort of laid out like a necklace or something like that. They appear like more like the necklace that you find in the bottom of the jewelry box, which is all tangled up and folded over on
Hmm.
itself. And it's a non-trivial problem to understand how did it get that way, and then how does it uh, get so for instance for DNA, I think it's quite a fascinating problem to say, well, DNA in the cell um, is all tangled up, but when DNA when you have the process of mitosis and the DNA reproduces itself, which is the fundamental mechanism of life and cell reproduction, well, you have to take these two different strands and separate them out. Well, something happened. I mean, especially if things are all knotted up, you have these strands that are tangled around each other. So there's clearly some bit of topology in that. Now, I don't know, despite some, I think, maybe somewhat grandiose claims by various people, no one's really solved this problem. So I don't think you can say that it's really been applied there. But 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 the ideas of topology are really present in even the phrasing of the question. So I think that's quite fascinating. I don't go to as many physics talks as I used to, but there was certainly a vogue for understanding some aspects of physical gauge theories. In other words, things that you can measure where the measurements were essentially turned out to be not invariants, where there's this idea of a Wilson loop, which was a certain integral as you went around a knot in some three-dimensional manifold. So that's a more physical part of gauge theory. So
Okay.
those things are interesting. I don't think you can really fairly call them a an application in the sense that I don't think no one's really solved the problem of how how proteins get tangled up. No one's really solved the problem of how DNA untangles itself. There have been interesting things and serious people both on the mathematical and biological side have thought about them. But yeah, that's where I see that maybe there's a chance that all this would be applied. The other thing I would say is, if you go back to the origins of topology, and this isn't necessarily all that low dimensional, but the idea. one of the reasons Poincaré was interested in topology was that he was trying to understand these classical problems of mechanics of several the stability of the solar system and so on. So if you think about that, what you really are thinking about is objects, I don't know, planets and asteroids and so on flying around in space. And so there's lots of interesting topology in those, especially if you consider the long-term aspect, because you sort of see the orbits of these things, and those are intrinsically three-dimensional. So Poincaré discovered all sorts of interesting stuff in that way, and he was led to think hard about topology in part because he was interested in these problems of dynamics. So I don't know. Again, I don't know that there's any great applications of um,
Okay.
low-dimensional topology in that sense. But topological thinking, yeah, sure, it's there. It's certainly there.
Sure. All right. Well, can I ask you about what is to you the most disturbing concept regarding the mathematical infinite? I have one if you want to
Yeah, well,
listen to it.
I've never found it particularly disturbing. I mean, I was, I mean, I was, I mean, I can go back to my earliest encounter with infinity, which was, as a child, I'm sure, an argument that I had with friends. I'm, you're talking about like 7 years old or something like this, where, you say, well, I can name you know, I'm 100 times stronger than you, or I'm 1,000 times stronger than you, or I'm 1,001 times stronger than you. And at some point, when you realize that you could just go on, and then someone would triumph by saying, well, I'm infinitely stronger than you, something like, this kind of childish things. So that's a disturbing concept because then someone would say, well, I'm infinity plus one stronger than you, or whatever it is you were arguing, you're better at baseball or something like this. I mean, so, that's a disturbing concept that, infinity plus one is no better than infinity. So, but that's a very naive thing. But, in terms of mathematics, the use of infinity or, sets of infinite size or you know, spaces of infinite dimensions. It's just part of the landscape. It doesn't, it's just there. I mean, it's not, I know people get all worked up about this, and there's all sorts of things about large cardinals, and people in set theory or logic um, can really make a whole production out of it. But to me, it's just an idea, and there's nothing disturbing about it at all. What's your example?
What I mean is the fact that the unit interval has has many elements as the whole real line. I can't
Ah,
really grasp my head around how this is possible. I have a more sort of a personal example relating to the concept of infinity and how I would approach to it as a child, as when I was a child, and it is the episode of sometimes when I was in bed and I was like probably around 10 or 12, yeah, probably around 10 years old. I would sometimes think, what if this could be interpreted as sad, but it's not sad. I would be wondering, what if I were dead? Because now I'm going to sleep, and if you want to interpret sleep as the sort of daily death, and you wake up the next day, after how many hours you're going to wake up. It's 8, 7, 9 hours that you're going to wake up, and then I would be wondering, what if I am dead? When would I wake up? And then I would keep on start counting. Would I wake up tomorrow? No. Would I wake up in 2 days? No. Would I wake up in 1 year? No. And I would just keep on going, just increasing the amount of numbers, and the sort of realization that this process would never come to an end. So there would not be a day I would wake up. Kinda gave me a lot of not anxiety, but in the sense a lot of worrying in that moment, because I would be like, oh my God. So basically, that's it. It's over. It's infinitely. I would say it's yeah. It is never going to be the case that I will be waking up again. And so yeah, I would say that probably that was my first encounter.
Well, thanks a lot. Now I'm not going to be able to go to sleep tonight.
Yeah,
Yeah, I don't
that's
know. I think it's some, in those terms, I actually find, um, although I I find the notion that the universe is finite, say both in space and time, to be much more troublesome than the idea that it's infinite. The idea of an
why.
infinite, well, just because, well, if you had, I mean, this of course is non-realistic because you have to think about how time is treated in relativity, especially if you have somehow finite space-time. You sort of say, well, okay, if time just goes on without end, that's okay, that's just the way it is. And it had no beginning. That's just, well, no beginning is a little bit troublesome, I suppose, also, but no end seems, oh, that seems okay. But if it has, but if it's not infinite, then I don't know, what does that mean? It somehow wraps around. I mean, mathematically, you can understand how that can happen. I mean, there are certainly solutions to Einstein's equations and so on manifolds that are not Euclidean space and that are periodic or something like this. So I don't know. It's certainly it's physically possible, but I find that very hard to not it's not disturbing. It's just that I can't, I don't understand the mathematics of how it actually can be or what the physics can be. This I find ideas of, recurring time um, much more philosophically that's a disturbing idea to me. Whereas the idea that, well, even if I'm not part of the world, which I for forever, which it clearly won't be, that the world itself just goes on forever. I don't know. That seems okay. That the world comes to an end that's much more troublesome.
Okay. How how do you come to terms with the fact that most of the interesting questions that you're probably working on, or that probably you are not working on, but you simply wonder about, for example, the beginning or end of time, how do you come to terms with the fact that these questions might never find an answer?
Well, I think some of these things are unanswerable. I mean, whether time is infinite or not is not a again, this maybe goes back to the beginning of the discussion. I don't I those things are just they're just things we won't understand. It's disappointing. It would be nice to know the answer to all these things. Um, I'm not actually all that troubled by it, other than it's, as I say, it's a sense of disappointment. We'd like to know, and we're not going to know. I mean, I'm not going to know the answer to much simpler questions, I'm sure. So, it's one of the things you come to understand as a mathematician is that most questions are hard. You can answer some of them, and you're happy when you do, and you're happy when you make those contributions. But mostly you don't answer most of the things I've wondered about over the years. I don't know the answer to. I mean, I had this experience just the other day. So I've just retired, and I'm supposed to clear out my office. And one of the things in my office was an entire drawer, a big long drawer full of notes, just notepads that I wrote ideas on, going back to the 1980s. And I would look at these things and I'd say, oh, yeah, I remember that problem. And I'd realize, well, probably I'll never know the answer to that one. So it you feel nostalgic, you feel a little sad. I mean, I certainly feel sad about some of the things that I won't whose answers I'll never know. But I don't know. I don't feel profoundly disturbed by the idea that we're not going to know the answer to these kind of big questions that you're posing.
I wanted to ask you, who is your favorite mathematician now, whether he's live or in the from the past?
Well, that's a hard one because there's a lot of people I really, really, really admire. I think from the deeper past is Riemann, but from the more recent past, but still who was someone who's still alive, was John Milner, and just Milner because Riemann because just of the incredible vision in laying out in a time when they just didn't have the language uh, or the correct way to phrase things, just sort of laying out the incredible set of ideas that and generating so much mathematics. But Milner may be closer to home because it just seemed like this guy just had one fantastic idea after the next, and there was a sort of I don't know how to there's a sort of elegance to the way he moved through mathematics. He just sort of saw something and thought about it and found the answer in a way that I would love to have been able to do. You know, it's so yeah. I don't know. You read. I mean, their paper. Some of my younger colleagues laugh at me. In fact, I have a little piece on this on my own webpage because I would tell them you have to. I mean, not even Milner's biggest papers. There was a couple of papers that I really loved that I learned a lot from as a graduate student, and and I told them truthfully, I read this paper every year. I sit down and I start at the beginning and I read it again. I mean, his most famous paper, Milner's most famous paper, is where he discovered the idea of exotic differentiable structures. In other words, on a sphere. In other words, which was actually the first example of any manifold where you had described differentiable structures as I was discussing before. And the manifold happened to be homeomorphic to the seven-dimensional sphere, but not diffeomorphic. And his paper it's 8 pages long. It's one of the most profound things that anybody ever did. It's 8 pages long. You can have a graduate student read it, and they can just sit down and do the whole thing. And you'd say, oh, well, okay, how could it's such a simple short paper, but it's so elegant and so brilliant and so insightful. So I don't know. That to me is an absolute. I just well, that's just the sort of thing you would just love to be able to do. It's just to take something and just see it so clearly that you could write down something revolutionary in the course of 6, 8 pages. That's an amazing thing to do.
Okay.
To me, it's a little like I don't know whether you know this, a famous line drawing of Picasso of Don Quixote, and he goes, just a few little bits of black ink, and it's unmistakable what he's drawn. And you just say, well, how did someone have the vision to see that? Because they saw the essence in the simplicity. So that's what I would compare that to.
What is the most beautiful idea in mathematics?
Oh, I don't know. I mean, there's so many.
The most elegant and at the same
Well,
time
I don't
profound.
know. I mean, I'll go back to what I said earlier, which is I would say the construction of the natural numbers out of nothing, out of the empty set, and I think that's an amazing thing. You
Okay.
know, that's I mean, there's many fantastic ideas and beautiful theorems and wonderful things, but I think if you're asking the most beautiful, it has to be something fundamental and basic. I don't know that I'm not sure I would commit to that one, but there's an answer for you.
Okay. All right. Well, thank you for this conversation, Daniel.
Yeah, yeah, this is fun. It's interesting to talk about all these things.
This was a conversation with Daniel Ruberman. Thank you for being with us. Thank you for listening. I hope you have enjoyed this conversation on mathematics. This was Back to the Stone Age.